Morning. Can you guys all hear me okay? You folks hear me? Okay, cool. So don't forget, Monday is exam 3. We're gonna run the same. We're gonna run the exam the same way. Homework 9 is due. I'm gonna change it to Saturday instead of Friday. Give you an extra day, but also so you haven't. I'd like to have you to have a chance to study on Sunday at least. So I don't want to really make the homework due on Sunday. I want to make it due on Saturday so you have time to study for the exam. The DC motor lab is due on the 25th, and then the oscilloscope lab I will talk about today in lab. That'll be due on the 13th. It's actually a pretty short lab. You basically just need to show me that you know how to use an oscilloscope. Okay. And today I just want to finish up Faraday's law. Whatever I don't finish here today, I'll finish in lab. Basically what I'll have left is some examples and applications. Does anybody have any questions before I get started? Or concerns? Oh, I got to email you a practice test. So let me email you a practice test. Okay. So let me write that down. That way I won't forget. Okay. The exam will be, the fourth exam will be like the first exam in that it'll have 5 problems and you will choose 4 out of the 5 to do. All right, you'll do 4 out of the 5. You will tell me which 4 the grade. So it'll be like the first exam. And the reason why I do that for this unit is, I feel this unit is harder, although I think it's harder than the second unit, but I guess it just varies by semester. And so I'm going to give you the opportunity to choose the problems you want graded. Okay, it'll still be a 2-hour exam, like the first 2 exams. The fourth one will not be like the first. The fourth will be more like the second, because there's more circuits in it. You know, and again, you want to think about the fact that I tend to make my questions more conceptual. Although the number of questions, the types of questions I can ask on the fourth exam is a lot more limited, because on the fourth exam we'll be doing RL circuits and mutual inductance and AC circuits, and the AC circuits analysis that we do is limited. You'll do a lot more when you take the Engineering 17 class. And really it's limited just because of the time we have. It's number one, it's the first time you'll be doing AC circuits, so we do some basic ones, and then we just don't have a time to do some more sophisticated circuits. So in that sense, there's less problems I can ask on the fourth test than I can on the second test, but the fourth test will be very similar to the second test. The fifth test that I gave this semester will be quite new. It should be a short test. It'll just be in chapter 39, based on whatever I cover in chapter 39. Okay? I hope that answer is sufficient. Other questions? So I did grade your redos, and you can see that, you know, for some of you it made a pretty big difference in your score, and I hope that you saw that those problems weren't that bad. They were really conceptual in nature. You know, what I want you to be able to do is to be able to understand the concepts and not just grind through math. I want you to understand conceptually what's going on in the physical system. Okay, and it's true that it is a little bit harder to write an exam when the course is online. So This is, again, this is really the first time I'm going through this process, so it's a learning process for me to learn how to write an exam for the online course. Okay. No questions, concerns? All right. So I created a video for the problem I did the other day, because there's a lot of questions regarding the problem with the solenoid and the induced field. So I created a video for it and I posted it on YouTube, and I sent you an email regarding it. So I hope you take a look at it, because I went in a little bit more details than I normally would in class, and that was based on the questions that was asked of me. So I hope I provided enough details for that problem. Okay. And I also hope that some of you guys got my email yesterday morning. I canceled office hours. I had to cancel office hours in the afternoon. And then I noticed I got an email on Zoom saying that there were people waiting for me. But I'm hoping you got the email saying that the office hours were canceled. Okay. All right. There was a question on this problem the other day. And the problem I did in class was straightforward. But then Patrick asked, what happens if I take this wire PQ and put it in a plane that's perpendicular to the plane of the board? So in other words, the wire PQ forms a plane that's perpendicular to the plane of this board. What happens? And people, and then, folks think, well, current's going to take the path of least resistance. Okay. Now, in reality, there's no resistance. There is some resistance in here. The resistance is not zero. So there still must be an electric field in here. It turns out that the electric field, and we'll be able to answer this when we do Lenz's law, the electric field can only be in the plane of the board. The induced electric field can only be in the plane of the board. It can't have a component parallel to the magnetic field, and it can't have a radial component. The video that I created actually kind of goes over, the video I created the other day for that problem regarding with the solenoid that I did in class, I actually go over that. If you have a component of the magnetic field, if you have a component electric field that is in the direction of the magnetic field, then you would have, you can choose a loop that is perpendicular to the plane of the board, integrate around it, and you get something that's non-zero. However, there is no changing flux through that loop. So therefore, E induced has to be zero. If you have an electric field that has a radial component that's induced, like this way, so imagine the wire was pointing straight up and down, then the electric field would have to have a component in the radial direction. You would violate Gauss's law, because there's no charges here producing an electric field. If you have an electric field that depends radially, Gauss's law, if you take the integral of E dot n dA, if you have a radial field, this integral is not going to be zero. That means you have to have charges there. We would violate Gauss's law. That means this has to be zero in the radial direction. There is a more formal proof of this, that the electric field that's induced is always perpendicular to the magnetic field. The electric field can't have any components in the direction of the magnetic field. This is borne out in Maxwell's equations, which I can't show here. Okay. But if you watch the video I created the other day, it'll make my argument that I just said here a little bit more clear. We're going to do something called Lenz's law in a little bit, and that's going to also help to explain why no current can go through here when the blue wire is in a plane that's perpendicular to the plane of the board. Okay. Yeah, and it also, I spoke to our department about this, and we want to build a demo now. We'd love to build a demo to show this. So that was a great question, Patrick. So let me do Lenz's law, and then maybe I can come back to here and then talk about this. Okay. Yeah, demo would be great. It's just, I don't know how long it would take us to build something like that, because we need a lot of electrical energy to build it. Okay, so let's go back and let's talk about what we left off with the other day. We started doing something called, or we started describing something called motional EMF. Basically, we have a wire on rails, and in this particular example, the wire, the rod on rails, the rod was moving to the right. There was a magnetic field into the plane of the screen. And what we noticed is that based on the force on the electrons in the rod, we would get, due to the magnetic field, we would get a current that circulates counterclockwise in this particular case. And if the field is uniform, then we show that the induced EMF on the rod is just the magnetic field times the length of the rod times the velocity there, or the speed of the rod. And that the current that's induced in that rod is just the induced voltage divided by the resistance. But because of the fact that this EMF is due to the motion of the rod, and in general we would call it a moving circuit, then we call this a motional EMF. And so we say delta V motional is equal to BLV rod. And I'm just writing this as a magnitude, okay? I'm just writing everything in terms of magnitudes here, all right? And then the current is going to be this motional EMF divided by the resistance. And of course the electric field that's due to the movement of the rod, due to the separation of charges, is just going to be V times B. And you notice in this problem that the electric field direction is perpendicular to the magnetic field. And it turns out in general that has to be the case. The electric field is being perpendicular to the magnetic field. Okay. Then we considered energy. We looked at energy considerations. So let me draw my rails with the magnetic field into the board. Let me put my rod of length L, and let's draw the magnetic field. I guess it's enough X's. And we said that the velocity was this way. The induced current is up. Okay. And they said that if this is the case, you have a current on the rod in a magnetic field. What is the direction of the force? Okay. The direction of the force can't be in the direction of motion, because that would imply that the rod gets faster without me putting energy into the system. I'd be violating the law of conservation of energy. Okay. The force on the rod has to be this way. And of course, We can prove this because we have a magnetic field into the board, a current upward, and you use I cross B, and you get that the force is in that direction. In fact, I can deduce the direction of the current without going through all the arguments that I did the other day with the separation of charge. Okay, if you look at the slide, I showed you how the charges get separated, and I show you how the current is induced in that slide. But I can actually deduce the direction of the current without going through that thought process. All I got to do is invoke conservation of energy. I know that the current that's induced has to create a force opposite to the direction of motion. That force is going to want to slow the rod down. Okay? So even if I didn't know this, I know that my force has to be this way. And then I just got to guess up or down which one gives me a force to the right when I use the right-hand rule. That force has to be in the opposite direction of the motion. I mean, think about it this way. I have an object that has kinetic energy, 1/2 mv squared. Then all of a sudden, I have energy that's being dissipated in my circuit, I squared R. Where is that energy coming from? The energy has to come, the electrical energy has to come from the motion of the rod. So that the kinetic energy of the rod, the mechanical kinetic energy of the rod, is converted into electrical energy. And so this thing then ends up having to slow down while we have energy flowing in our circuit. Okay. This is the velocity. Maybe I'll write V rod, sorry. If this is hard to see, I'll write V rod. Okay, sorry about that. Does everyone understand that argument? And the fact that energy is conserved in these kind of problems is an important statement. Okay, it's an important statement. Hold on, let me go to... We went through and actually did the energetics the other day, so I'm not going to go over this again. The direction of the current that's induced here satisfies something called Lenz's law. Lenz's law says something about the direction of the induced current in these systems. Okay. So what does Lenz's law say? Lenz's law says that the direction of the induced current opposes the change in magnetic flux. Okay, the direction of the induced current opposes the change in magnetic flux. So what does that mean in this particular case? Well, if the rod is moving to the right, what's happening to the magnetic flux? The area is getting bigger, the area exposed is getting bigger. So our area is getting bigger, B times A is getting bigger. So B times A, so our flux is getting bigger. And so what we want is, we want to induce a current that wants to maintain the status quo. The induced current wants to maintain status quo. It doesn't want to increase the flux. It wants to bring the flux back to where it was. So that means the current has to produce a magnetic field that induced current has to produce a magnetic field that opposes the change in flux. So right now, if the rod's moving to the right, the flux is increasing because this area gets bigger. But the induced current, if I use the right-hand rule, produces a magnetic field in here that's out of the board, which is against the increase in the change in flux. Does everyone see that? I points up. If I wrap my fingers around the rod, the magnetic field comes out of the screen towards you folks. So as the rod moves this way, the flux due to the increasing area increases, but then the induced current produces a flux out of the board, which tries to oppose that change. That minus sign that you see in Faraday's law is really a statement of Lenz's law. The problem I did the other day in the video, I allude to Lenz's law. I don't say it explicitly. Okay, but when you look at the conclusion of the problem I do in the video I posted on YouTube, I'm really, what I'm trying to do is really state Lenz's law. Okay, that the induced electric field in that problem was opposite to the direction of the current. Let me just check a question. So it says, can this be thought of in the same way as throwing an object up in the Earth's gravitational field, except that the decelerating force is not constant? Yeah, I'm trying to understand what you're trying to say in this question, Andrew. If you throw an object up, gravity is going to try to pull it down, right? It's not going to speed up on its own unless you put energy in it. Is that what you're trying to say? The object is not going to speed up on its own unless you put energy in it. In fact, that's the same thing as if you take an object and you throw it out in outer space, it's not going to go any faster unless you put energy into it, correct? So you can look at it that way too. But basically, you can't get more out than you put in. That's basically what this is saying. You can't get more out than you can put in. There's no way. I mean, it would be nice. It would be awesome is if I just gave this thing a push and then this thing accelerated to the right. It would really, if we could violate conservation of energy, it'd be awesome. Okay? Just think of the applications. Imagine making a car like that. Okay, so this next slide, I just talk about what happens if V is not perpendicular to B. In this example that I've done here, I've assumed V is perpendicular to B. And I said that E motional is V times B, but that's the magnitude of it. In reality, if I wanted to write this as a vector, it's a cross product. And then I would have to integrate this around a closed path to get the motional EMF, which is what you see in the slide. So integrating this around a closed path will give you the motional EMF. Okay? So if you're interested in doing problems where V is not perpendicular to B, then you would have to use it. Now remember, this came from the Lorentz force. This came from the fact that we invoked the following equation. And I set this equal to 0 so that the electric field is equal to V cross B. Well, the electric field is opposite the B cross B. Let me put it that way. Okay, that's where this came from. And so then the integral of E dot dl is your delta V. And yeah, we're not going to encounter problems like this, but it just FYI, good to know. Okay. So one of the things I'm trying to show you here is that we've described an induced EMF occurring as a result of two different methods. One, you have a moving circuit, and another from a changing magnetic field. It's one of those few phenomena in physics where the law can be explained in more than one, based on more than one physical principle. There's two physical principles that can be used to describe what's going on with Faraday's law. One is a circuit could be moving, another one is a magnetic field is changing. And that is embedded in the equation d phi dt. When you look at delta V as minus d over dt, that information is actually embedded in there. But you have to use some mathematics to actually be able to bring that out. And this is not described in your textbooks. Okay, actually there was a person who wrote an article about this and said, hey, we can write it this way. So if you apply some vector calculus and Leibniz rule for differentiating integrals, you can write this integral, you can break this integral up into two parts. And the two parts that you get, as you see in the slide, maybe I'll make the slide bigger. Give me a second here. Well, I mean, you mean those two terms, Patrick, you mean those two terms are equivalent? I can use either one of those two terms, right? I can actually have a circuit that's moving in a magnetic field that's changing. So both of them will take into account my changing flux. Yeah, it'll take care, it'll account for both. Okay. So in this particular, in the problem that I did with the rod, my dB dt is 0. And so when I do this integral, it's going to come from my emotional EMF. When I do this integral, it'll come from my emotional EMF. But I will show you the example, but it's not going to be explicit in the way I write it. Okay. So this is kind of an interesting way to actually look at it, which is really not described in the textbooks. Oops. So in our particular example, if we look at this particular example, the flux is B times A, the flux through this loop. But B, now remember, I'm going to be just taking the total derivative directly. So you're not going to see the cross term come in. You're not going to see me actually break this up into two parts. I'm going to take the derivative directly. The area is just going to be, this distance we'll call X times L. And then d phi dt, since this is constant and this is constant, that's the only thing that's changing. This gives me that. And again, the minus sign that you would see on the screen is because of Lenz's law. I didn't put the minus sign in here, but I just took the derivative of the flux with respect to time, just to show you how this works. But what I did here is I just took the total derivative. But if I broke this up into, if I looked at it conceptually, step by step, you would see that the first integral would survive in that slide, and the second integral will not, because the partial of b with respect to time is 0. So, really, to summarize, the induced EMF can arise because of either moving circuits or changing magnetic fields. When you have a moving circuit, then you really need wires. If you have a changing magnetic field, no wires are required. That's like this problem. So let's apply, for this problem, let's apply Lenz's law. If the magnetic field is increasing into the board, remember, this is a solenoid. Let's say the magnetic field is increasing into the board. Lenz's law says you want to produce a current that opposes this change in flux. In other words, I want to produce a magnetic field out of the board. So that means, using the right-hand rule, the current's got to do this. So the current is going to go counterclockwise. The current's got to go counterclockwise no matter whether I have this blue loop here or in the plane perpendicular to the board. Imagine if this was in a plane perpendicular to the board. Then what? Imagine, how is the current going to go through here if this is in the plane perpendicular to the board? In fact, let me do this. It would be the same as if I took a rod, a wire, and just connected it from here to here. And you say, well, that's a direct short. Well, there's no power supply here, right? You're saying that's a direct short. The current has to be counterclockwise. If the current goes through here, how are we going to get counterclockwise current in this loop and in this loop? How is that possible? And this is what I want to demonstrate. What is the potential difference between these 2 points? So if the lights stay on, they should be different. Right? If the lights stay on, the potential difference between these 2 points is going to be different. Because if it's 0, then neither one of these go on. If it's 0, then there's no current at all in my circuit. But that would violate Faraday's law. Because Faraday's law says I have to have a current going like this. The electric field is in this direction. Okay, the electric field has to be, it turns out the electric field has to be perpendicular to the magnetic field. It cannot have a component in a radial direction. If the current went this way, it would have a component in a radial direction. You violate Gauss's law. Now, granted, that's a subtle thing, especially at this level, at the introductory level. But that's what would happen. So like I said before, we have 2 different laws to explain how EMFs are produced. Suppose we have an airplane moving at constant speed through a uniform magnetic field that is directed perpendicular to the plane's velocity. So I can't draw planes very well, but I'm going to give it a shot here. Okay, and then let's have a magnetic field. We're in the sky, okay. Our viewpoint is from the top of the plane. We're in the sky, all right? And there's a magnetic field. What's going to happen? Well, because of F is Q, V cross B, the wings that are made out of metal, the charge is going to separate. And in the interest of time, I'm not going to go through all the details of how the charge is separated. But you will get separation of charge here. So you will get a delta V across the wings of the plane. But you're not going to get a current because you don't have a complete circuit. Okay, you don't have a complete circuit. So you're just going to get charge separation on here and that's it. And there is no flux changing across the wings. The magnetic field is uniform. And again, the induced EMF comes from this. Like we did for the rod. Now, what if we replace the plane with a loop? Let's replace the plane with a loop of wire in a magnetic field. So here's a loop of wire. And we'll place it in a magnetic field. Again, we'll make it into the board. Doesn't matter if it's in or out. Now what happens? Because of this, you will get separation of charge. Here and here. You will get a delta V here, and you will get the same delta V here. The electrons can't go because the rods are in this direction. The electrons aren't going to do anything in this direction. So there's no EMF induced here. There's no EMF induced here. Is there going to be a current in that loop? Oh yeah, Morgan, the V is the velocity of the plane, just like the V was the velocity of the rod. So, but you have the same potential difference here and the same potential difference here. Are you going to get current? In other words, this point and this point are at the same potential. Right? This point and this point are at the same potential. You have the same system as basically the airplane. Okay, you're not going to get any current going through there. Now, if the magnetic field was changing, or if maybe part of this rod was in the magnetic field, then yeah, you would get a current. Because the delta V here and the delta V here would be different. If you had a changing flux, you'd have a current. The moving circuit is a little bit more complicated. You have to actually, for a moving circuit, if you want a current, you do have to have a changing flux. Okay. Suppose I have a wire carrying current I. This is the Lenz's law problem. What is the induced, what is the direction of the induced current in the loop? So let me draw my wire. And let me draw my circuit. Above it, now this wire, if I use the right-hand rule, is producing a current into the board, right? Okay, so let's start with that first. So if the current is constant, the flux is not changing. So let's let di over dt be bigger than 0 now. Let's let the current increase. The magnetic field then increases into the board. Lenz's law says that the induced current in this loop, because the flux is changing, has to oppose the changing flux. So that means this loop has to produce a current such that the induced field is out of the board. This current produces a changing flux that opposes what's happening, because this is going to produce a magnetic field out of the board because of the fact that the magnetic field is increasing into the board. Does that make sense? That's true. The magnetic field is decreasing. But I guess your question is, what is your point regarding that, Morgan? You gotta remember, there's two different things. There's one, we're talking about time dependence of the field, and one that has to do with position dependence of the field. The induced EMF has nothing to do with position dependence. The induced EMF has to do something with time dependence. Does that make sense? Is that okay? So a lot of times when we say constant, why is the flux changing? Because I'm changing the current. Right? Isn't the magnetic field due to this wire mu naught I over 2 pi r? And I'm changing I, so then the magnetic field changes, right? This is the magnetic field. So dB dt is going to be bigger than 0. Okay. All right, so let me try another flux problem. And I just got to check my time. Hold on a second. So I have a tube. I'm getting something off a magnet. The magnet's really strong, so I can't pick it up. Hold on a second. Okay, here we go. So I have a copper tube. This is a copper tube. And I'm going to just drop a ball in a copper tube. Normally I can do this with 2 tubes, but it's easier to see this in the class. So you're going to have to listen for the sound when I drop the ball through the tube. You tell me how fast this was. Did you hear when it hit the ground? Of course, now I lost the ball bearing. So you heard that, right? Okay, so now I'm going to take a magnet. This is a magnet. It's a pretty strong magnet. And I'm going to drop it in the copper tube. You ready? And I'm going to try to catch it. I don't know if you can see it. Got it. Do you notice the time difference? It's way slower. Why is that? Why is it way slower? Right? This is not a magnet, right? It won't stick to the copper tube. Copper is not magnetic. Yeah, the magnet induced the current in the copper that opposed this magnet. So it actually, if the North Pole was facing down on this magnet, the current would be produced so that you have a North Pole facing up. And that would produce a resistive force so that this thing goes down at a much lower speed. The acceleration is much less. Now, one can sit there and actually, there are some people who actually go through and do the mathematics of this problem. It's actually quite complicated to do the mathematics. It's not the easiest problem in the world. But this is a Lenz's law problem. For us, you just need to see it as a Lenz's law problem. Here's another example. I can't do this one here. This is one I do in class. Although the one that I do in, the demo I do in class is not truly a Lenz's law demo, because I actually have to use the AC power supply. I don't have a DC power supply on campus that will allow me to do this. But let's pretend we have a DC power supply. And I have my little circuit with a wire wrapped around an iron core. Of course, what's the purpose of the iron core? Well, the iron core becomes magnetized when you run a current in a loop of wire around it. And that's going to enhance the magnetic field. On top, I have a red ring. Okay, you see that red ring on top? When I close the switch, what's going to happen? When I close the switch, I'm going to energize this magnet. When I close the switch, di dt is going to be, that's right, di dt will be bigger than 0. You're going to produce a magnet here. And that's going to induce a current in the red ring. Just like in the demo I did, it's going to produce a magnetic field that opposes the magnetic field in the green iron core that you see there. And so generally what happens is the ring jumps. I can't do this demo at home. I don't want to mess up my ceiling. In fact, it works great when you take the ring and you stick it in liquid nitrogen, it jumps even higher. Because what happens is when you put the ring in liquid nitrogen, its resistance is even lower. You have a much higher current. And so the force is much bigger and that thing really just flies off. You can maybe try to find a demo online. Okay. Suppose I drop a magnet through a ring. It doesn't have to be a ring. It could be a coil of wire, and it can attach the coil of wires to a voltmeter. You can actually measure the voltage that's induced by dropping the magnet through that coil. And it's interesting, if I just drop it, whoops. If I just drop it, the voltage looks like this. Maybe I'll exaggerate it. Hold on, let me exaggerate it more. There. That's what the voltage looks like. This is when the middle of the magnet passes through. Why is this one taller than this one? If I just drop it through, why does that happen? Yeah, it's moving fast, it's accelerating, right? Because you're dropping in the Earth's gravitational field. So it's going faster. So V is going to be bigger, so your induced EMF will be bigger. Now, if you this can be, I can also have it, it can also be like this. Just depending on which pole of the magnet goes first. Okay. Now, if you look at the second case, what happens? If I were to measure the current, suppose I were to measure the current, in which case is the current going to be higher? Well, it turns out that in the first case, the left case will be higher because I have a lower resistance. By putting a notch in it, I'm increasing the resistance. I'm increasing L. And so the current will be lower. In fact, the demo with the ring, this demo, if you put a notch in this ring, it might not go up. Because you've increased the resistance dramatically. These currents that are induced in the conductors, they're called eddy currents. The demo I did and those two examples I showed you are examples of eddy currents. And sometimes they're not wanted and sometimes they're useful. In motors, they're not wanted. In transformers, they're not wanted because they produce heat. But there are some cases where where they're important. Now, in a transformer, what you can do in a transformer, I'll give you a simple picture of a transformer. Here's an iron core. We're going to talk about transformers in a week or two. And let's put some windings here, some windings here. Okay. When I run a AC current here, a voltage is going to be induced here, but there's also going to be a current going through the core. This is going to get hot because of I squared R. However, if you take this transformer, which has a thickness coming out of the screen, and you laminate it, and then glue the pieces together, now you will have an iron core that has a higher resistance, and so you're gonna make R bigger and I smaller, and so you're going to reduce the heat that's produced in this core. Where would you want to use eddy currents? Where would they be useful? Anybody driving an electric car? Yeah, magnetic braking. All right? You run basically a metal around the magnet, and that's especially in your wheel to slow it down. Yeah, generators too, right? When you have magnetic braking, when you have an electric car, what happens when you slow down too? What happens to electrical energy? Where does it go? It charges the battery. So you can use magnetic braking. So eddy currents could be a good thing. Anybody have an induction stove? You can heat things up. How do you folks charge your cell phone batteries? Have you ever seen the fancy cell phone chargers now? You don't have to plug in the phone. You just put it on a charger. Yeah, the inductive charging. A lot of applications of this idea. Okay, before I well, let me talk about this. I wanted to do some demos, but let me keep moving. I'll do a demo in a minute. Consider this system. The green circular loop of wire rests on the table, and a long straight wire lies on top of this loop, directly over its center. The current I is increasing. What is the direction of the induced current in the loop? That yellow wire is along the diameter of the green loop. What do you think? Describe the flux below the wire and the flux above the wire. Anybody have anybody want to hesitate? Want to guess what the answer is? No, it is 0, right? It has to be 0 because below the wire, below the yellow wire, the field's coming out of the loop. Above the yellow wire, the field is going into the loop. And since you're along the diameter, half is going in, half is going out. So the total flux is always 0. And the field is symmetric about the loop. So yeah, the total flux is, there's no induced current. So that's a trick question. They cancel out, that's right. Okay. Before I do some problem, let me just go over some of the applications, and let me come back to these problems, because I'll use the remaining time here and the remaining time in the lab to go over these problems. Okay? I just want to make sure I cover all the concepts, and really I have. I'm just doing applications. So for this problem, isn't the magnetic field below the yellow wire coming towards you? And isn't the magnetic field in the wire going into the plane of the screen? And so you have half going in, half going out. The flux is always 0. So I hope I explained it again okay. So let me bypass this. I have some nice problems. One's a railgun problem, but let me demonstrate the Faraday's law. Not Faraday's law. Let me demonstrate the eddy current to you. Just give me a second. I don't know, somehow this is like one of my favorite demos. So let me set up my camera, my other camera. So now the sound quality is worse. Yeah, I know. I'm changing cameras. Can you see now? Okay, yeah, I had to change cameras to do so I have a pendulum, and this is aluminum. This is aluminum. Okay, so just in case you don't believe me, this is a magnet, and these are pretty strong magnets. Aluminum is not magnetic, so this is a piece of aluminum. It's not magnetic. Okay, this is a magnet. Just so you believe it, that that's a magnet. Okay. All right, so I have this thing, and it swings. You can see it swings fairly freely. Now I want to take a magnet and show you the effect of the eddy currents. Let's let this swing. Oops, I screwed that one up. All right. You see that? Because it keeps banging. Hold on a second. I got to release it properly. Okay, it pretty much stops. Without the magnet, in fact, look at that. If I move the magnet around, without the magnet, it just swings freely. Now, if I increase the resistance in here, so let me get you a different one, if I can find it. I'm going to use just the same size, but I've cut some slots out, so I increase the resistance. I'm going to reduce the current. It will still slow down, but not like in the other case. That's the effect of the eddy currents. So good question, Morgan. Where is the current being induced? The current actually circulates in here. The current circulates within here. It actually goes, it's not a circle, but it circulates in here. It will probably do something like this. The current is going to be complicated because the magnetic field in reality is fairly complicated in this magnet. It's not perfectly uniform. And so when I cut it like this, now I'm increasing the resistance. So the current has a longer path to go through. Oh, that's a good question. Guess what? I have this. It makes a little bit of a difference. It's hard to see with this one. This magnet is so strong, it's actually hard to see. Yeah, I was going to show you this just because of the interest of time, but since you asked, it's still pretty fast. I think if it was heavier, it would go through. But if I increase the separation of the plates, I mean the magnet poles, it goes a little bit further, but it's hard to tell on the camera. Yeah, it's not like the solid one. The solid one's like it just stops dead in its tracks. Okay. To me it's kind of a cool one. No, that multimeter, I have a generator that I'm going to show you in a second. This is my area for doing demos, so I have too much. I have the scopes here and all kind of stuff. So, anyway, you will see the multimeter hopefully soon. All right. All right, so let me go back to the PowerPoint and talk about applications. You can see the PowerPoint, right? Okay, good. So, like I said, there's a lot of applications. This, to me, is like probably the most interesting course chapter in the course because of the numerous applications, as you see listed there. The one big one is really the generator. Typically in textbooks, they also talk about the pickup coil for the guitar. So you have basically a magnetized string. When it vibrates, it's near a pickup coil. You have a changing magnetic field that the pickup coil experiences. That means that EMF is induced. The signal goes to an amplifier. It's processed, and then it goes to a speaker, and you hear sound. You can take a loop of wire and rotate it in a magnetic field. Now, in the case where you have a loop of wire and you're rotating it in a magnetic field, the flux is constantly changing by rotating it. The angle between the normal to the loop and the magnetic field is constantly changing. So let's pretend that the magnetic field is uniform. That picture is ideal. I mean, the magnetic field that you see there is really not uniform, but let's pretend that the magnetic field is uniform, just to make the math easy for us. And then you have that loop of wire. We're rotating it in the magnetic field. So the angle between the normal to the loop and the magnetic field is constantly changing. So let me go on the board. Let me draw a couple of pictures. So here's a loop. Let's say the magnetic field points towards us. Let me draw the loop when it's at some angle. So this is a side view of the loop. So let's say the magnetic field points, and we're looking towards it. I'm sorry, we're looking at it from the side, sorry. So the magnetic field is going this. The normal to the loop is this. This is phi. So the flux then is B times A times cosine of phi because of the fact that we're taking the dot product. Okay. We're assuming that A is constant and B is constant just to make the math simple. If we rotate this at a constant speed, then phi is omega times time, where omega is the angular velocity. And so phi then, phi sub B is B times A cosine omega t. So this is a loop of wire. The magnetic field is coming towards us. That's the normal to the loop. So let's look at it from the side. And I'm doing it at an angle. If we look at it from the side or from the top, either way, if you look at it from the top, you're going to see a magnetic field pointing outward. You're going to see your loop, one of the sides of the loop, and then the normal is also parallel. When this thing rotates, then there's going to be an angle between B and the normal to the loop. All right, pretend this is the plane of the loop. The magnetic field is coming towards you, and then the magnetic field stays in the same direction, but this loop changes direction. The normal of the loop changes directions. Does that make sense? As it's rotating, the angle, what I'm trying to illustrate is there's an angle between the magnetic field and the normal to the loop. So you can have, the black could be the direction of the magnetic field, and the purple is the normal to the loop. And so the angle between the markers is phi. Does that make sense, Morgan? Yes? No? I'm hoping I answered your question. I'm not sure if I answered your question, Morgan. What are you confused on? The angle, or just focus? Don't focus on the picture I drew on the board anymore. Just focus on what I have here. Okay. So here, the purple is the normal to the loop. The magnetic field is, let's say, pointing towards you. The angle between the purple marker and the black marker is phi. Do you see that? Or not? Correct. The flux is max when the normal to the loop is parallel to the magnetic field, right? The dot product depends on the dot product. This depends on the dot product between B and N. And if they're parallel to each other, then take a zero. Cosine of 0 is 1. Correct. Right, when they're perpendicular, there's no field lines going through the loop. Isn't that true? Okay, and that's the thing. So when phi is 90, there's no field lines going through. So that's phi then as a function of time. So the induced EMF is the derivative of this. So let's take the derivative of this function with respect to time. In fact, the negative of the derivative. And so I want a minus d phi sub d over dt. And that's just going to give me, when I take the derivative of this, I'm going to get a minus sign. I'm going to cancel the minus sign. So I'm going to get b a omega sine omega t. That's for one turn. For n turns, for a loop of n turns, now we have a generator. That's how we generate electrical energy. Okay? And this term, when we're considering what's coming out of your wall socket, this number is about 170. And then omega is 2 pi times 60 hertz. So imagine rotating that coil 60 times a second. So this is where AC power comes. Or they don't have to be permanent magnets. They can also be, well, yeah, I mean, you're right. You want to use permanent magnets. I have one here. Omega is the rate at which the angle changes. It's called the angular velocity. Right, I mean, that's from Physics 205. It's the same concept as from Physics 205. So, this is how electrical energy is generated for your homes. You have basically a loop of wire that's rotated in the magnetic field. And this is done by turbines at the power plant. Electrical energy is generated. The energy goes up to a step-up transformer so that it's sent through high voltage. And the reason why you do that, you send high voltages, is because you're transmitting the energy over long distances. The wires have resistance, and so you're trying to. Just give me a second. The wires have resistance, so if you increase the voltage, you reduce the current. So I squared R losses are reduced. Okay. And so then by the time it gets to your house, you step the voltage down to your 240, it's brought into your house. So that's the ones. So the amplitude of your signal coming out of your outlet is 170 volts. If you had a real oscilloscope, not the ones you're going to be using for the lab, please don't use the ones for the lab to measure the voltage out of your socket, because you'll destroy the oscilloscope. Okay? Because those oscilloscopes are only for 50 volts max. If you had a real oscilloscope, you can actually stick them into your outlet and measure the voltage. The reason why we use AC instead of DC is that you actually, the average power loss is less for AC as opposed to DC. And whether you use 50 hertz or 60 hertz, Europe use 50 hertz, it really doesn't matter. So let me demonstrate to you the AC generator. Good question, Morgan. So the voltmeter measures, and we'll talk about this in 33, an average value. This color root means square value. So it measures 120. The oscilloscope will actually give you the voltage as a function of time. You can actually see a trace of the voltage as a function. You can see many cycles. So you can see the maximum voltage. It'll actually plot out the sine function. The voltmeter will not. The voltmeter just gives you an average number. So if you want to look at signals that vary with time, you use a oscilloscope. That's the difference. Okay, so let me switch to the camera. Here's our generator. This is the motor that I used the other day. Let me turn it on. Now, this is not a very efficient generator, okay? Because this is, I don't have a turbine rotating this. It's going to be me rotating it. So what I'm going to try to do is see how much voltage I generate. Because I have an electromagnet here, so I got to actually plug in the power supply. Okay, let me make sure this is working okay. I did this the other day. The most I can generate like 0.2 volts. Okay, so I'm going to rotate. What I'm going to do is just give it a big push. So as I give it a big push, you can see the EMF that's induced. But guess what? This is actually a DC. The way I have it set up is for DC motor. Because I'm turning it slowly, you can actually see it change as a function of time. If I was doing this 60 times a second, you wouldn't be able to see the change. That's where you need an oscilloscope to look at the trace of the voltage. I have it set up as a DC because of the split commutator. If I use a slip ring, now I'm generating AC voltage. And you can see it changes sign. It goes from plus to minus. Okay, I can't move it fast enough. However, I have a generator for which I can actually produce enough voltage to light up a light bulb. So here's a little generator. These are like toys. Let me move my motor. I guess I should turn off the power first. So here's a little bit of a generator. I turn it, light goes on. And one of the things I said is that the motors and the generators are kind of like the motor is a generator running in the opposite direction. So I actually have two generators here. And so what I'm going to do is I'm going to connect one generator to the other. Let's see what happens. And of course, it's always easy to demonstrate in class. Because in class, I would actually give these to you so you can play with them. Okay, so what I did was I connected one to the other. So I'm going to spin one. I got to do this right. Right? Can you see the other one spinning? Actually, I got to take the light bulb out. I'm not sure why it's not working. There we go. Do you see that one's moving? Do you see that the generator is causing the motor to move? So I was running this as a generator, and this one as the motor. So a couple of things to think about this. Think about it. First of all, when I have this unconnected, it turns out that it's actually very easy to turn. If I hold one still and try to turn the other one, right now I only have two hands, so it's for me to do that. Sorry. I would probably have to. I would probably have to put a very large torque on this. I don't want to mess these up, but if in that particular case. If I just turn it like this, it's actually very easy to turn. But then when I put in the bulb, sorry, I'm going a little bit over. When I put in the bulb, it's actually harder to turn. Why is that? It actually, you can actually feel a difference. It's actually harder to turn this when I put the bulb in, as opposed to when there's no bulb in. Why is that? Yeah, I am doing work to make the light bulb go on. The current, it's really not a counter EMF, but it's a counter torque. So you have now your loop of wire in the magnetic field, but now a current is running through it. So you have a current running through a loop of wire in a magnetic field. That's going to produce a torque. And so the counter torque is going to be NAI induced right from U or N cross B. Okay. And of course the magnitude of it is going to be that. This is the angle between the area of the loop and the magnetic field. And that's because of conservation of energy. You're trying to deliver energy to something. Your light bulb is, you're putting energy into the light bulb. That's what, just imagine, simple-minded way of producing electrical energy at the power plant. Just imagine you are turning the generator by hand, or let's say a bunch of people are turning the generator by hand, okay? And now you start connecting your generator to a bunch of air conditioners. The energy you're putting in is being used up by the air conditioners. So you actually have to do more work to crank that generator to produce the same amount of energy. You'll actually feel it. If you're cranking that generator at the power plant to keep the air conditioners on, you would actually feel it getting harder and harder to turn. So you have to actually put in more energy to keep it going at the same rate. I don't know if you noticed in the video, when I turn the generator, the motor did not turn it at the same rate. That's because of the counter torque. And this is a reflection of conservation of energy. So let me just tell you the difference between the DC generator and the AC generator. I know I'm going a little bit long. When you have the split ring commutator, the voltage looks like this. When you have an AC generator, the voltage looks like this. And you see that in this picture. This is an AC generator. If I had a split ring commutator, then every time I reverse I turn the loop by 180 degrees, I reverse the direction of the current. So this is an AC generator, which is an AC motor running in reverse. I want to mention one more thing, and then in lab, I'm going to go through all the examples I skipped, okay? So, one more thing I wanted to say about this idea. Suppose you have a drill, Did you ever notice that the drill runs hotter when it runs slowly? Did you ever notice if you're drilling something that's really hard to drill through, that when the drill runs slowly, it gets hot? Why is that? Well, when a motor is running, you do have a loop of wire rotating in a magnetic field. When the motor runs faster, the induced EMF is going to be greater because of this turn. If it rotates faster, this is going to be bigger. So a motor, when it runs, let's say 120 volts, it'll actually generate something called a back EMF as a result of Faraday's law. And what that does is reduce the current in the motor. So motors like running at their normal operating speed. They don't, in fact, when they start up, they actually draw a lot of current. As they go faster and faster, the back EMF increases. This turn gets bigger and bigger until you get to its operating speed. And that's when the total current that the motor draws is minimized. And so the last equation that you see there, the total current that the motor draws is the voltage you apply to the motor minus the back EMF divided by the resistance of the motor itself. So for a motor, like a drill, I total is delta V minus the back EMF, which you'll write it with the script E divided by R. This depends on how fast your motor is turning. If it's not turning very fast, then your total current is going to be basically delta V over R. Which means you're drawing more current, more power is being used up, it gets hotter. All motors are like that. When they start up, they draw more current. Once they get to their natural operating speed, then they draw less current because of this current. And you do have homework problems on this. By the way, the homework, except for the last two problems, the homework should be fairly straightforward, I hope. Except for making sign errors. Okay, so I'm going to stop here. You have any questions? I'm going to do the problems I skipped in lab. Because I've covered everything. The rest is just doing examples. All right, I'll see you folks in lab.